when it comes to all this stuff with the Riemann sums, we eventually are going to be taking the limit as n goes to infinity of a giant sum. Okay? And the sum of the area of the rectangles. Okay? So today we're going to go back to reviewing a whole lot of things about this sigma notation, as well as give ourselves some more kind of some more foundational work for dealing with sigma notation and summation in general. Okay? All right. So the first thing I want to talk about is the meaning of the sigma notation. So in general, sigma notation starts with an index, and that index tells you which terms you are adding together. So I look at this one, and I want to say what this really tells me is I want to do 2 times something plus 2 times something plus, and those somethings are the numbers, the integer values in between this number and this number, the bottom and the top. Okay, so this would become 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And I know I am done when I've reached the top number. Is everybody good? Now, we can calculate what that is. It works out to be 30. Everybody good? Okay. So if I'm doing this one, I'm going to start with 2 times 0 plus 2. And then 2 times 1 plus 2. And then 2 times 3 plus 2. And then 2 times. Anyone got a problem with what I'm doing? What's the problem?
You skipped 2?
I skipped 2, yeah. Oh, come on.
It's the way I copied all that down and didn't even notice. It's awful.
And guess what this answer is?
30.
30. It's the exact same sequence. Do you guys see why they're the same sequence?
It's the same quantity of.
It's the same number of terms, and 2 times 0 plus 2 is the same thing as 2 times 1 plus 2. It's different starting value, but still adding together the same terms. Okay? All right, what about k squared? What would that become? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Which is something. I think 91. Somebody smarter than me should figure that out. You guys know there's a math shortcut to doing the summations?
Isn't it like math? Yeah, I'm gonna try it because I know.
Math 0?
Math 0.
Yeah.
It's math 0.
X is equal to is 6.
That wasn't from intelligence. That was from... Oh, I could make it from...
91. I
Would
totally
you just write x squared in the summation on here?
Mm-hmm.
It's like
No. I'll take care of this.
not even funny.
Do you not have a calculator?
City charge at my house.
There's very little more I could do for Nate at this point in terms of, but I'd rather you be able to follow along. Yeah. Everybody good? Are we feeling okay so far? Okay. How's this one different?
It's a variable.
There's an N, okay? And, okay, right? So in some respects, the number that we are consistently filling in for in this case is K. I know that because the index tells me it's K. All right? So I have 1 over N times 1 squared plus 1 plus 1 over N times 2 squared plus 1 plus 1 over N times 3 squared plus 1 plus all the way up to 1 over N times N squared plus 1. I will be the first to admit that you cannot put this into your calculator. Everybody okay? So, this is why we have to learn the reasoning processes that we're going to be learning so that we can take those summations when we need to take the summations. Okay? Because on top of that, essentially where we will go for this is we're going to take this expression and find the limit of this expression as n goes to infinity. And the minute I throw that limit there, this just becomes what was a hairy problem became a monster of a problem. So the skills that you're going to learn today, which you guys are going to be like, why do we need to learn this? You need to learn this to take these limits. And this is how you use the limit definition of an integral to take a definite integral, which is what we will be doing pretty much forever. We'll be doing definite integrals for the rest of the year, or for the rest of the semester. Definite integrals. And indefinite integrals. But all right. Lastly, this one would be the sum is I equals 1 to n of f of x1 delta x plus f of x2 And without giving too much away, each of these values is an area of a rectangle on a graph. Like the height of this rectangle is f of x, the width is delta x. So that's where this is going. Okay? That being said, I don't expect you to come up with this equation yet. Just know that it's coming from our definition of what the definite integral is. You guys already know about integrals being area. We're going to prove everything this week is about proving that. Everybody okay? All right. It can also be useful, and this is something that'll come up a lot next semester. It can also be useful to find a sum using sigma notation. So in order to do this, we have to find two things. We have to find our bounds, and we have to find an equation that models this sequence. So, you guys, are you with me that I can look at this 3 and say that the first term was 3, the second term was 5, the third term was 7? Okay, and what's happening between terms each time?
They're going up by 2.
Going up by 2. So if I'm like trying to find the equation that models this, I know my equation is going to have a 2n in it. That 2n is saying add 2 for each one. And what am I adding to? 2. So what value what value would I put here so that when I plug in that 1, I get 3? 1. So this sequence is 2n plus 1.
Why is it not 2k plus 1?
Oh, it is. It's 2k plus 1.
Sorry, I just-
What should the top number be?
M.
Well, n,
3.
it's n, but we need to know which n this is. 2 times what plus 1 gives me 23? 11.
Wait, is it N?
N. K is what you're plugging in. N is the whatever the last one is. N is the last one. So for the very last term, N and K are the same thing.
So N is the top number, like the upper bound?
N is the upper bound. And then you guys, what did you get? 153?
Sure.
I just plug it in the calculator, right? 133? 143.
It's not
193.
Is that in the hundreds?
Pi. 2e to the I pi power.
143.
143. All right, let's look at this one. This one's a fun one. What is my last term?
Well, so it's gonna be, is it 2/3 K? Or no, it's not. It's hard to do the last term, I feel like, before you know the.
No. In this one, it is easy to figure out the last term. I have 1, 2, 3, 4, 5 terms.
So it's the fifth one, n equals 5. Oh, I thought.
I'm adding the first through the fifth term, and now
I don't even know how you first.
6/7 equals 5 times something.
you guys, is there a pattern going on here?
Yes.
Yeah.
You add 1 each time. So, are you guys with me? Are you comfortable looking at the pattern of the top and the pattern of the bottom separately? Can we do that? What's the pattern on the top?
Up by 1.
K plus 1. So that this is 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1.
Oh my gosh, and it's k plus 2.
And then the bottom is K plus 2. Are we good? Is this making sense?
Yeah, I don't know why I didn't think. If it has the dots, you have to like count it.
So overall, it's K plus 1 over K plus 2.
Is k always 1 at the start?
No. It's usually 1 or 0.
Why is it 1?
Because it's easier for you guys to see this as the first term, the second term, the third term, the fourth term. Right?
I suppose.
I could just as easily. The sum of K equals 0 to 4 of K plus 2 over K plus 3. But that's like not as helpful to you guys.
In like a problem, would we be given the k value to start at?
No, you're not going to be given this to do.
Okay.
This is me laying the foundational work for when we get to the calculus work.
That makes more sense.
So I don't want you to stress about coming up with these. I do want you to recognize that coming up with these can be helpful. Because now, I don't know about you guys, but I would not have wanted to type that into the calculator. That feels like an annoying thing to do. But using the sigma notation doesn't feel as bad. Especially if we're looking like at a 10-term, 15-term sequence. Did anybody type this in?
547 over 140.
Sure. Works for me. Okay. Okay. I will be the first to admit for this next piece, it would be easier to just plug these into the calculator versus what we are going to do. Okay? I know that you can just type these into the calculator. I am laying the groundwork for what's coming next. That's all I need you to know right now, okay? All right. So these formulas at the top will be given to you. Okay? So, essentially, what happens is that in this scenario, n equals 9. Is everybody comfortable with me saying n equals 9 because it's the top index? And all of these are starting with k equals 1. Okay, so these are written for starting at 1. Okay? All right, so 3k plus 2 becomes, well, that 3k becomes 3n plus 1 over 2. Plus, the 2 becomes 2n. And this is me using these first two formulas.
And these are given to us.
You will be given these.
Sorry, I just can't remember.
You don't know where I'm going with this. You don't get too excited too fast.
Where did you get the
Why is
2
the
and 3 at?
So just the k alone. The k alone is n plus 1 over 2. So 3k is 3 times n plus 1 over 2.
Where'd you get the plus 2n?
The plus 2 becomes,
CN.
you notice my sigma's gone. Yeah? Now, what do we know that n is? In this case, it is 9. So this summation is 3 times 9 times 10 over 2 plus 2 times 9. Yeah, Hannah?
Where'd you get the 3N?
The 3, this 3 is right here, and then the k becomes this whole thing.
Oh, so K is equal to, or I guess, whatever it is equal to N times whatever. You just put that 3 out front because it's a constant that goes with it. I see.
Okay, you guys. From there we have 135 plus 18 is, I think 153.
Yeah.
Same thing you would get if you typed it in. I would like you to use these formulas for now because I want you to practice them for when they start to matter. Okay? Because there are going to be times where it's no longer that you know n equals 9. I'll leave it as n. Okay. So what would k, so for this one, you guys, what would k squared become?
N squared times N plus 1 squared over 4.
No.
Or no, wait, the other one. The
N
times N plus 1 times
n plus 1,
2N plus
2n plus 1 over 6, minus, what's going to happen to that? 5? 5n. What's n?
1 or 12?
In this case, it'd be 12.
Why is it 5 times 6 instead of 5?
I don't know. That should be a 12.
Okay.
I think it's 590.
How did they come up with this?
It's more that they did it a gajillion times and noticed the pattern and said, hey, the pattern makes more sense than trying to take this out over and over and over again. Okay. Remember I said eventually we're doing this for n amount of rectangles and we don't know what n is. Okay. For something like that, instead of our summation being this term plus this term plus this term, we write the summation so that it is an equation with respect to n. Okay? So, what if I'm doing this one, what will the k become? So k would be the equivalent of this expression, yes?
So you just put that in plus 1.
So it'd be n plus 1 over 2. What would happen to the 1?
1n.
1n over. That n squared is just like a constant that comes along for the ride. We don't know what n is, but we know that it's always the same number. N squared would always be the same number. Every good? Now, the whole purpose of this is to come up with a simple expression. So I'm going to multiply this by 2 over 2 to get rid of that fraction within a fraction because that's messing me up. So I have it n plus 1 plus 2n over 2n squared. Can you guys think of anything else we could do to maybe simplify this a little bit more?
Take out an n.
Okay. If I take that n out, okay, I would have n plus 1 plus 2 over 2n squared. Yes?
Cancel out.
So I have n plus 3 on top and 2n on the bottom. For those of you who I think would take a different approach than taking the n out, you could also think of it as if I distributed that n,
Oh, you could factor.
and then I'd have n squared plus 3n over 2n squared, and then take an n out. And I'd still end up with the same place. Okay. All right. So you guys. If I asked you, what is this sum if I'm going to 5? Guess what I'm going to get? You could either type this into the calculator now, or you could just say overall the answer is 8 over 10, which is 4/5. It's a shortcut to getting to, all right, no matter what n I'm plugging in here, I'm going to end up with this expression. It's a shorter expression to get there. All right, now, if we keep in mind that eventually our goal is going to be the limit as n goes to infinity. Which limit would you rather take, the blue one or the green one? By far, right? Okay, so the goal in what we are doing is to be able to rewrite this as this, so that when we have to take that limit isn't going to make us so angry we are going to explode. So the whole idea is we're trying to prevent explosions. Everybody good? See, I'm done for the day. I told you to.